Hi everyone, I'm Anish and welcome back to PrepFusion. So today we'll be starting the lecture 4 for frequency response using polar plots, right? Basically in previous lecture we learned about a bit about polar plot, right? What is a polar plot and how to plot it, right? And also we solved few questions with the polar plot, and also we understood the type and the poles, all those things we understood, right? The concept we were clear. So now, right, what we'll do, here, right, we did few key point also, that in the end of the lecture that I told you that polar plot will not be a unique representation for a OLTF, okay? Because like if I want to go back to my transfer function representation, right, to my OLTF from my polar plot, then I can get multiple transfer functions, right? Multiple transfer functions. So polar plot is not will not be a unique representation, okay? So that those things got clear. So in this lecture, what we'll do? In this lecture, we will go a step ahead. That is, we'll understand about the relative stability parameters of OLTF. So you might ask, like, what are the relative stability parameters? Stability parameters I do understand, but what is the relative? Okay, and also it is for the OLTF, not for the CLTF, not for the closed loop transfer function. And why is that? Why is that? Basically, right, we want to predict the if we vary our OLTF, then what will happen to my stability of the system? Okay, basically then what will happen to my stability of my CLTF, closed loop transfer function? Okay, because mainly what will happen in plant transfer function, right, will mainly vary the OLTF itself, will not touch the feedback system. Okay, will not touch the feedback because it will be a unity feedback anyways, right? Mainly touch the OLTF itself. Okay, so if we change the this OLTF, generally we will change the OLTF itself. So by changing the OLTF, how is my stability getting affected? That's why all of these things we are studying. Okay, like the practical purpose I'm telling you. Okay, but like theoretical, obviously we'll study. Okay, so let's understand what do you mean by relative stability. Okay, first tell me, I have like two systems, right? S1 and S2, where S1 and S2 are the closed loop poles, are the closed loop poles. Okay, closed loop poles of system 1 and 2. Basically system 1 and 2, S1 and S2 are closed loop poles. So what are you noticing here? Like, what is the question? The question is, which systems are stable? Here I have two systems. Can you tell me which systems are stable? Okay, you might say, sir, like both of them are on the left hand side of my S plane, so obviously both of the systems will be stable. And I will say, yes, you are correct. Okay, no guessing work here. Yes, both of the systems are stable. But why did I take this question? Because it is very simple, right? So basically, until now what we have been studying, okay, until now, like, we have been studying to answer this question only, which system is stable. Okay, basically until now we have been studying absolute stability. So absolute stability. Okay, up until now we have been studying absolute stability. Now what do I mean by absolute stability? I have, I think, told you also previously, but again I will tell you that by absolute stability, right, by absolute stability I mean this will give me a simple one word answer, yes or no. Is my system stable or not? Yes or no. Okay, so this will give me a simple yes or no, basically a boolean answer, right? So yes or no. Okay, so stable, simple yes or no answer. Okay, but sometimes, like here, right, like what is the answer? What is the answer for this one? Answer is here both are stable, right? Both are stable. Okay, so just wait, let me check if everything is recording or not. Yeah, it is recording, right? So here, right, both are stable. So what I can say is, here both are stable. Okay, so here both are stable. Okay, so yeah, this is this one. So like the answer of this question is both are stable. Now let's go to another question, and from there we'll basically understand the concept of relative stability, right? So what is the next question? Next question is, which system is more stable? Now you might ask, how is this possible? Can a system be more stable than this one? Both are stable, but sir, why? How can we tell if the one system is more stable than other? What is the parameter for that one, right? Or is there anything like more stable? You might say the both are stable, right? There isn't anything like more stable. Both are stable, okay? Or you might say like S1 is more stable than S2, or you might say S2 is more stable than S1. Whichever answer you tell, right? You have to justify yourself. Why are you telling that S2 is more stable than S1, or why are you telling S1 is more stable than S2? Okay, so like intuitively, okay, if this is asking which system is more stable, what does this mean? What does this mean? Like let's say, like this is the ideal control system, right, where nothing varies. The temperature doesn't vary, everything is ideal, so nothing varies. There is no variation in my OLTF, right? There is no variation in my OLTF. But in practical systems, what do you see? Like when we go to do the lab measurements, right, we do theoretical results and do the practical results. We always see that practical results are not exactly coming like theoretical results, right? There is some error in between them. So the pole's location S1, whatever is the pole location, there may be a bit of variation due to some temperature variation, due to something, right? Due to some error, due to some like external disturbance, right? Due to some external perturbations, what may happen is my pole location may vary a bit. My pole location may vary a bit. So what will happen? If my pole locations vary a bit, let's say my S1 pole location, like it will just vary a little bit, right? The error, generally what you see in my lab results, right? The error is very small, right? So if the error is very small, so it will lie around this region itself, the S1 region itself, but it will vary a bit, right? It will vary a bit. The variation of S1 will be capped in this one, okay? The error is very small. Now, what about the variation of S2? What about the variation of S2? So S2, right? S2 can vary like this one, okay? S2 can vary like this one. So S2, there is also some error in the system too also, so there can be some variation like this one. What are you noticing here? So if my variation is bit too much, then what is happening? Like during the error, right? In some cases due to less tolerance of the system to due to variations, my pole is going on to the right hand side of my S plane. So what does that mean? That means that the system is becoming unstable due to some variation, due to some error, okay? System S2 is becoming unstable. But can system S1 ever become unstable? Obviously it can also due to variation, but the chances of it is very low because the variation is generally very less, right? Tiny amount. Hence this one going crossing the imaginary axis, the chances are very low. At least the chances are very very low than this system 2 at least, okay? System 2 has higher chances of crossing the imaginary axis, right? Hence the system may become unstable here. So what does this mean basically? This means that my system 2 is less stable than system 1, or I can say my system 1 is more stable than system 2. Okay, my system 1 is more stable than system 2. Why? Due to variation, and due to variation in system 2, few like sometimes my pole may go into the right hand side of my S plane or may cross the imaginary axis. Whenever there is some crossing of the imaginary axis, right, or the j omega axis, obviously it is shifting from left hand side to right hand side. Obviously then what will happen? My poles will lie on the right hand side of the S plane and my system will be unstable. That is established, right? So I have written few key points about relative stability here, right? We are telling that system 2 is more tolerant to parametric uncertainty due to system dynamic. Okay, this is not sorry. This will be actually system 1. I have written it wrong. Okay, uh, yeah, this will be actually system 1. Okay, and this will be system 1 again. sorry for that. Okay, where am I going? This will be system 1. Okay, I'll just read out key points there, will understand. So system 1 is more tolerant to parametric uncertainty due to system dynamics modeling errors, right? So if there are errors, system modeling dynamics error, all those things, like there will be some uncertainty, there will be some variation, right? And system 1 is more tolerant to that. So even if the error is larger, right, it isn't crossing the geometric axis, so my poles are still on the left hand side of my S plane, so then still my system will be stable. But for the system 2, right, system 2, what is happening is that if there is some uncertainty, right, large variations, then it is crossing my imaginary axis. If it is crossing my imaginary axis, then obviously what will happen? Then obviously the system will become unstable, which is undesired, right? So hence system 2 is less stable than this one. Okay, like hence system 1, okay, system 1 is relatively more stable than system 2. Okay, hence system 1 is relatively more stable than system 2 basically. Okay, now system 2 is more oscillatory in nature as it has relatively more overshoot than system 1. Okay, what does this mean? So you just take simple example. Where have you where have you listened or uh, taught, where have you learned the term overshoot, right, in the time response chapter of second order system, right? Second order system. So let's assume both of them are second order systems, and if my S2 poles are lying over here, what does this mean? This means my this theta, right, theta is theta from this axis is very high, right? Theta is very high, okay, from this. And if you do cot theta, what will happen? My overshoot will be more. Zeta is less. If zeta is less, then my overshoot will be more basically. Okay, so if zeta is low, my overshoot will be more. Okay, and here, right, my zeta is high, so my overshoot will be less. Here it is giving me more overshoot, so it is going like outside the steady state point bit more, right? It has more of a oscillatory nature. So if it goes more on the right hand side, right, and touches the imaginary axis, what will happen? My system will become oscillatory, right? So overshoot will be I hope you know, right, overshoot will be 1 itself, right? 100% overshoot, right? So yeah, so this S2 has more oscillatory nature, second order system. I hope you remember, right? Again, right, you have to revise, keep on revising. If my zeta is here, this zeta is less than this zeta or something like that, so this zeta omega n is less than this zeta omega n, then what will happen? Okay, all those things you have to keep in mind, keep on revising, right? Keep on revising. Like you can relate with theta itself, like theta itself, right? Theta, it was e raised to power minus pi cot theta, my MPO, maximum peak overshoot formula. So I hope, like, keep on revising, right? You just couldn't forget the previous chapter. You study and then forget, that is of no use, right? You have to crack the exam, right? And for cracking the exam, obviously you have to keep on revising the previous subject, keep on solving the questions of previous subject. Very, very important, right? So yeah, this one is this one. So S1, S2, all those things, yeah. So S2 has more oscillatory nature, so that's why obviously it will be less stable than system 1. So all these things are telling us the same thing, but I told you in 3 different ways, okay, how to tell the same thing basically. Okay, so what is the next point? So the next point, what it is telling us is that as system 1 is relatively more stable than system 2, then the dynamic response of system 1 becomes lower. Okay, what does dynamic response mean? The response between the, like, the transient response is, it is telling between the steady state and just after giving the input, right? So dynamically, right, this system 2 will be much faster because it has more oscillatory nature, right? So it will obviously reach its first 100% of its steady state, right, at first point, to reach much faster, t rise, or you can say, then it will go up, go down, and like that it will go on. But okay, so the dynamic response of system 2 is faster, but what is the thing? The settling time, right, settling time of system 1 is better than system 2. Why? Because, like, just a brief approximation here, like you can say the real part side, this is omega zeta 2 omega n2, this is zeta 1 omega n1. Okay, zeta 1 omega n1. Okay, so yeah, now, right, now basically what is happening, this is like, let me write here, let's name this as, let's name the real parts, right, zeta 1 omega n1 and zeta 2 omega n2. Okay, so this is basically what my real parts are. Now, right now, what is happening? Now, if I take the inverse of this one, what is the time constant? Time constant is proportional to the magnitude of my inverse of my reciprocal of my negative real root. So, like zeta 1 omega n1 is greater than zeta 2 omega n2, right? So now if I take the inverse, then my tau 1 will be greater than, sorry, will be less than tau 2. Okay, that is for sure, right? Because time constant will be less than, like, first s1 will be less than s2. So I'm just taking the inverse, or taking both this, swapping this two, right? So now, right, now what should I do? Now what should I do? Basically, right, now what is my settling time? What is my t settling? My t settling is basically directly proportional to time constant itself, right? Tau, right? Hence my settling time of 1 will be much less than settling time of 2. So yes, my system 1 is settling much faster than system 2, but the dynamic response, right, basically the steady state response, it's good. System s1 is good, right? It is settling much faster, but the dynamic response is better in s2, right? So there is a bit of trade-off, because like initial rise time is very good for s2. Why is this important? So basically, initially when you turn on the fan, right, you want your fan to reach basically at least 80% of your steady state value very quickly, right? And that is what my dynamic response is, right? So that's why we can say, like, sometimes you have to do a bit of trade-off here, right? So s2 has better dynamic response, but s1 has better steady state response. So yeah, like this you can understand. So I will just take this one and take it to next page, then, so that I won't delete it. Okay, so basically, right, the t rise, so I'm just giving you a brief approximation. The t rise of 1 will be greater than t rise of 2. Okay, this is for sure, but it will settle first. Okay, so like uh, what I can say is, system 2 will have much faster dynamic response, and this does help, right? Sometimes, like, I want, like, to get the initial push, right, initial throttle. Basically you are in a car, right, and if you give the acceleration, or if you give the start, right, initially you want it to have a good starting torque, just like a machine itself. Machine also, you want your machine to have a good starting torque, like the induction machine or like the synchronous machine, right? All those things should have a good starting torque, right, to initially take the load, right, take whatever load there is. So it is very important. Okay, so from here we can understand that system s2 will have much faster dynamic response. Okay, so that is, we know. So you have to have the perfect balance, right? Whether you want too much of relative stability, or whether you want good dynamic response also, all these things, that's what a good control engineer does, right? He understands and respects what things he need to pick, right, and have a balance between all those things. Okay, so let me take this one and make this one a bit smaller. Okay, so this one is this one. So now, right, let's understand. Now I told you about the relative stability, but how will you measure them? How will you measure them? I told you, like, if there is some variation, this is more stable, like this is s21 is more stable than s2, but how do I quantify that? We have to quantify that. I just simply told you by visualizing it, but how can I actually quantify that, right? So here, right, how do I measure the degree of stability? What parameters are there to measure the degree of stability of a closed loop system? Okay, with the help of OLTF, that I didn't mention here. So what is my transfer function? My transfer function is y of s upon r of s equals to, basically it is a closed loop transfer function, right? So it is a feedback system, so it is g of s upon 1 plus g of s into h of s. Okay, so this is what my uh, transfer function is. Okay, so like now when will my system become unstable? Let's try to do that. So first I will write one equation, right? Like these are my poles, like whichever values of s satisfy this equation, right? This is the characteristic equation. Whichever values of s satisfy this equation, at that particular values of s, like I will get poles, right? I will get poles. Okay, these are my poles, like characteristic equation. And this helps us to find the poles, right? Now whichever values of s are satisfying this equation, basically they will be my poles of CLT, right? Poles of CLT. Now what is the interesting fact? The interesting fact is that, let's say I put s equals to j omega, so I'm giving some sinusoid input, right? I'm giving some sinusoid input. Okay, so I'll put s equals to j omega. Then what will happen? Like if I put s equals to j omega, like I'm giving some sinusoid input, so I want to measure the sinusoid response, right? Steady state sinusoid response. And then what will my OLTF become? OLTF also I have to replace with g of j omega itself, or you can replace it in the transfer function itself, h of j omega, right? Which is equals to, like, equals to -1. So I'm taking this one as, taking this plus 1 in the right hand side, so this becomes -1. Now what is the interesting fact? For like any value of omega, right? For any value of omega, for whichever this is satisfying this equation, what does that mean? That is, that value of omega is a crossover frequency. We already studied that in root locus, right? That value of omega is a crossover frequency. If it is a crossover frequency, what does that mean? That means it is either crossing from the left hand side of my s plane to the right hand side, or it is either crossing from the right hand side of my s plane to the left hand side, right? So any of these two things can happen, right? But it is a crossover point, right? So either anywhere, right? Anywhere, if this point is getting satisfied, then definitely what I can say, like if any, for any value of omega this equation is getting satisfied, then definitely I can say that my system will be unstable, right? System will be unstable for few values of omega. So why? Because what does this mean? This means I have a crossover frequency, right? Crossover frequency. Now if I have a crossover frequency, what does that mean? That means two things, right? So one is, if I'm going from here to here, okay, or another is like let me name this as g omega sigma. Another one is like this one, it can go from right hand side to left hand side. In both these cases, right? So for some values it is unstable, right? For some values my system is unstable, right? Okay, that I can confirmly say, right? That I can confirmly say. So for some values my system is unstable. Okay, so whenever I get a crossover frequency for some values of s, my system will be unstable. So for some values of s, my system will be unstable. For both of these cases, if I have some crossover frequency for both of these cases, uh, my system will be unstable. So this is the basically boundary condition. Boundary condition, right? Boundary condition. Okay. So like I'm getting crossover point, right? I'm getting crossover point. So what does this mean? Like what is this g of j omega into h of j omega? This is basically the what OLTF, right? This is basically the OLTF. And what I am doing, I'm just plotting the OLTF, right? So whenever my OLTF passes the -1 point, right? Passes the -1 point, what does that mean? That means my system will become unstable. My system will become unstable. If it doesn't pass the -1 point, that means my system won't be unstable. Okay, my system won't be unstable. Okay, so yeah, that is one thing. Okay, but how do I quantify that one? Okay, how do I say which one is relatively more stable than the other? Okay, even though both are stable, let's say both of them, like I have two LTFs, both of them doesn't pass this -1 point, right? Then how can I say which one is more stable than the other? Let's come to that point. Let's come to that point, right? So what I can say is basically I can take again two axes, right? I can take again two axes. Okay, so let's say this is real part of g of j omega into h of j omega, right? So again let me copy this one. Okay, so this is this one, right? So this is this one. Now like what else can I say? Now let me draw the polar plot for two systems. Okay, two systems. So I'm drawing the polar plot. Let's say this is system 1, right? System 1. Okay, both of them are similar polar plots only. Okay, similar shapes only, but the magnitudes are different. Okay, for different points. And let's say this is my -1 comma 0 point, right? -1 comma 0 point. Now let's name this as system 2 and let's name this as system 1, right? So if I name this one system 1 and system 2, what does this mean? Basically, right, can you tell me which one is more stable? Which one is more stable? Can you tell me that? So basically what I can say is this S2, right, is less stable than S1. Why? Because this S2, right, is more closer to -1 than this S1, right? So if there is some variation, okay, first this S2 will cut the -1 point than the S1, okay, than the S1. S2 will cut the -1 point basically, okay. So yeah, that's why this S2 is less stable than S1. So S1 is relatively more stable than S2, even though both of them are stable because both of them are not cutting the -1 point, right? So there is no crossover point as such. But if there is some variation, this will vary more, right? This will vary more. This has more room for variation, right? This has more room for variation. Hence, my S2 will go to -1, right? First, okay, and I'm assuming this is like a decreasing function only. Okay, I'm assuming this one. So my number of poles will always be greater than the number of zeros, and my magnitude will always keep on decreasing instead of increasing. My magnitude will never keep on increasing with respect to variation of omega, right, from 0 to infinity. So that's why, because my number of poles will be always greater than or equal to number of zeros. Okay, that's why. So yeah, that is that one, right? That is that one. So from here I can justify that system S2 is less stable than S1. Why? Because this is more closer. This has more less tolerance of like of not reaching -1, not reaching -1 if there is some parametric variation, right? Okay. So here, right, what I can write is that S1 is more closer to oh sorry, S1 is more stable S2 as S2 is more closer to point minus 1 comma 0. Okay, so S2 is more closer to point minus 2 comma 0. Now like that I again like quantified this one, that S2 is more closer, but how can I exactly say, how can I sorry, that one I just visualized you, but how can I quantify, right? How can I exactly say that yes, according to these parameters S1 is more closer than S2? How can I say it? Basically closeness can be measured in two ways, like this condition, right? I hope you remember this one, right? This one also came in the root locus, and from here, right, we derived two conditions. Just try to remember what two conditions were there. We derived, one is the angle condition, another one was the magnitude condition, right? I hope you remember, right? So closeness can be measured using two ways. Okay, so can be measured using two ways. What are the two ways? Basically the angle condition and the magnitude condition, right? So again I will copy this equation. So I'll have two conditions basically. The first one is generally the magnitude condition. So first one is the magnitude condition. What does this mean? G of G omega equals to 1 itself. And what is the angle condition? This is minus 1, right? So where is this point? This point is lying around here. So what is the angle from the positive radial axis? It is 180, or you can say minus 180, right? Generally we write minus 180, so that is the convention. It is the same only. If you write 180 and minus 180, it doesn't matter. So what is my angle condition? What is my angle condition? G of like at that particular frequency, right? H of G omega equals to minus 180. So I can measure the closeness in two ways. I can see at some particular frequency how close it is to my minus 180 degree. Okay, and at some particular frequency, when is my magnitude getting 1, right? When is my magnitude going to 1, and when is my like the phase angle getting to minus 180? Okay, so like how will we like understand this like one slowly? If we proceed to the lecture, you will understand, right? So it may so happen these two occur in different frequencies. Okay, these two will occur in different frequency. Okay, when my magnitude is 1, that frequency will be different, right? Here, right, my magnitude can be 1 anywhere, right, from between here, right? And here also my magnitude can be 1 anywhere between here. Okay, anywhere between here. And here, right, my phase can be like minus, it is reaching, both of them are reaching minus 180 at the same infinite frequency. But this, like if it is a, let's say this is a type 2 system or type 1 system, right, this can reach phase 180 minus 180 much faster than this one. Okay, much faster than this one. Okay, then what we can say, is that this S2, right, will be less stable than this S1. Okay, so yeah, if you increase the type system, stability reduces, right? So yeah, so these two, right, can occur in different frequencies. Okay, slowly just bear with me, just study the whole topic, right, then you will understand why these two like frequencies are different. Up until we complete the Bode plot, right, there you will totally get the complete idea of why is this called like this one and this is called like this one. Okay, we'll understand. So the frequency at which my magnitude becomes 1 of my OLTF, that is known as the gain crossover frequency. So I can write it as omega g. Okay, gain crossover frequency. Okay, and the frequency at which my angle of my OLTF becomes like minus 180, it is known as the phase crossover frequency. Okay, known as the phase crossover frequency. Okay, these are the terminologies. We have to understand this, we have to learn this, right? So slowly we are learning these terms, right? So gain crossover frequency is known as the frequency at which the magnitude of my OLTF becomes 1. Okay, simple, like the name suggests for itself, right? And what is my phase crossover frequency? My phase crossover frequency is the frequency at which my phase of the OLTF becomes minus 180 degrees, right? The phase of my OLTF becomes minus 180 degrees. So yeah, this is actually degrees. Can I write this one? Degrees. Okay, I won't be able to write this one. Sorry. I'll later change like that symbol, right? So the names are self-explanatory. Now let's understand the parameters of like relative stability. The closeness of my this g of g omega h of g omega to minus 1 point in imaginary versus the real, like basically polar plot. Basically the polar plot, right? Basically the polar plot, right? Basically will tell me about the relative stability. Okay, the amount, like the more close it is, the less relatively stable it will be, because more variation there will be, so it is more susceptible to touching the minus 1 point. And if it touches the minus 1 point, then what will happen? Then obviously my system will become unstable, there will be some crossover frequency. Okay, so yeah, this was basic brief about my gain crossover frequency and phase crossover frequency. Slowly as we get along this chapter, all your doubts will get cleared, don't worry, right? So now this is the first question, right? Very simple only. So what you have to do is, like you have to find the gain and the phase crossover frequency for the following OLTF. OLTF is given, just you have to find the gain and phase crossover frequency. You can simply find it. This is just simple mathematics, no concept at all. So pause the video and try to solve it for yourself. Okay, now I will start. What is the gain crossover frequency, right? So gain crossover frequency is the frequency at which my gain of my OLTF becomes 1. Just do that. Okay, so this is at gain crossover frequency. Omega equals to omega g itself, right? Omega equals to omega g itself. Now let me put the value of this OLTF, right? What is my OLTF? OLTF is this one, and put s equals to j omega here, right? So I just want to directly write the magnitude. So this time, right, I will do it faster because we have done polar plot, we've done everything, right? So can I directly write the magnitude? Yes, I can, right? So what I will do, this is 1 over j omega, right? 1 over j omega. So this simply will become omega g, because I'm replacing like omega with omega g, times like this, times under root omega g square plus 2 square. So it is omega g square plus 2 square, which is 4, right? So this is this one, this is this one, right? So yeah, which is equals to 1 itself, which is equals to 1 itself. Now from here we have to calculate omega g. Generally, right, what happens is, generally calculating gain crossover frequency is difficult. Why? As you can see here itself, how to find omega g? What I'll do, I will square both sides, right? If I square both sides, what I will get? In the left hand side, I will be left with omega g square into omega g square plus 4 equals to 1, right? Equals to 1. So what does this become? So what I will do now, this will become a quartic equation, right? order, or like polynomial of order 4. Obviously I don't know how to solve quadratic equations, so what I will do, I'll replace this omega g square, right? I will replace this with x, then I will proceed. Let's see. So I will replace my omega g square with x. Okay, so now if I proceed, right, now if I proceed, what is happening, like this equation will become 1 over x, and x plus 4 equals to 1 itself. So this is x square plus 4x minus 1, right? X square plus 4x minus 1, this is equals to 0. Now simply solve this equation, right? Solve this equation, solve the value of x. Okay, so if I solve the value of x, Sridhar Acharya formula, so this is minus 4 plus minus b square 16 minus plus 4ac divided by 2. So this is minus 4 plus minus 20 divided by 2, right? This is 2 plus minus, okay, minus 2 under 5, right? So I am getting two values. Now what does this mean? This means that my x is like some value. Okay, what is under root 5? So let me just find out what is under root 5. Okay, and let me just find the values, right? So this is under root 5, this is 2.23, and we have to subtract it. So I will get two values of x from here. One is minus 4.23 and another one is basically 0.23, right? 0.236, right? This will 236 and this will 236. Okay, so yeah, like I'm getting two values now. So what is the thing, which one, sorry for the disturbance, which one will I choose? Which one will I choose? I will choose the this one, right? I will choose this one. Okay, why will I choose, sorry, I will not choose this one, I will choose this one. Okay, why will I choose this one and not this one? Why? So what was my x? What was my x? My x was equals to omega g square. Now this, right, this is a positive quantity. Okay, omega g square will be a positive quantity. Why? Because omega g is real, as omega g real, hence is a positive quantity, right? Omega g square is a positive quantity basically. So if omega g square is like sorry, so hence this x has to be, hence my x has to be greater than 0, right? Hence I will reject this one and I will accept this one, right? X has to be greater than 0. So from here I can understand that my x zero point 236, and if I do the under root of 0.236, right? If I do the under root of this one, so like my omega g, so obviously I have to do under root, right? Omega g will be under root x, so my omega g will be simply 0.48588, 0.4858. Okay, so or you can write like 0.46, but that is fine, radians per second. Okay, so yeah, this is what my omega g value is. So one part of the question is done. What about the next part? So the next part, right, next part is to find the phase crossover frequency. So this one was used to find the gain crossover frequency. I should put the heading over here, part 1. Gain crossover frequency, right? What about the phase crossover frequency? Now the second part is Okay, second part is phase crossover frequency. So how to find the phase crossover frequency? So again, right, if I just paste it, yeah, again at phase crossover frequency, right, my angle of h of g omega p, like my angle of h of g omega h of like all this, right, at omega equals to omega p should be equals to minus 180 degrees. Okay, should be equals to minus 180 degrees. So this one is this one. Now what is my phase actually? So can I write it directly? Okay, now I'm writing directly because I've solved these types of questions hundreds of times. I replace s equals j omega, so I can do one thing here. I can write, like for your simplicity, 1 by j omega plus 2. Okay, I can write like this one. So now the angle contribution due to this is 90. The angle contribution due to this is tan inverse omega by 2. Tan inverse omega by 2. So this is in the denominator. So what will happen? I will get minus, right? So this is tan inverse omega by 2. So what is this? Like, but I need it equals to so let me first simplify it further. Okay, let me keep the minus sign outside itself. I need this one equals to minus 180 itself, right? So I need this one equals to minus 180 itself. So minus 180 equals to this minus 90 . So again, right, minus will get cancelled. I will take this 90 over here. Okay, if I take this 90 over here, 90 will be equals to tan inverse omega p by 2. Now for what value of omega p I get 90 degrees with tan inverse. So one value is possible, that omega p tending to infinity. So here, right, my phase crossover frequency is infinity, right? What does this mean? This means this never cuts the 180 degrees, right? This never cuts the 180 degrees. Okay, this never cuts the 180 degrees. So like this one was it for this question. Okay, so like I have taken few more questions and few more parameters I want to define, right? Few more parameters I want to define, but all of those parameters, right, we'll understand in the next lecture. So in this lecture we did very small things, but what did we learn? So main concept that I wanted to tell you is that about the relative stability parameter. Up until now, what we have been studying in Routh array, Routh-Hurwitz array, right, in time domain analysis or everywhere else, right, we have been understanding about the absolute stability. What does absolute stability mean? Absolute stability means that I am getting some simple true false answer, yes or no, answer, right? So either is my system is stable or it is not stable. Okay, true false answer. But I have to compare between two systems and I have to choose between two systems. So I haven't given, as a control engineer, I haven't given two systems. I have to choose between those two systems, right? Tell which one should I choose. But I have to define some parameters, then only I can choose, right? Like the time domain parameters also I have to take into consideration and about the stability factor also. So why does this happen? Due to some parametric variation, due to some practicality, right? Non-idealities. This variation happen, right? My poles may not lie exactly at this point. They may vary due to temperature variation, whatever there is variation, right? So yeah, hence that may occur. Now I have to choose between these two systems, and from these two systems, what I can say is S1 is relatively more stable than S2. That I can say, right? So if S1 is more stable, how can I quantify it further? How can I quantify it? So like these things I learned that yeah, Danny response will be slower for this one. That is one drawback. That is okay. But how can I quantify? I again go back to that mother condition, right? This condition is very important. The characteristic equation, the poles, right? Now this is some frequency, right? This is the frequency response basically. Now if at this frequency I am getting -1, what does this mean? This means I have a crossover frequency. This means I have a crossover frequency. For the sinusoid steady state response, I have a crossover frequency, right? So if it is a crossover frequency, what is happening? What is happening? Like I am crossing from left hand side of my S plane to the right hand side of my S plane, or from the right hand side of my S plane to the left hand side of the S plane. So if that is happening, then either it is going from stable to unstable, or it is going from unstable to stable. So unstable is the common factor, so it will always be unstable. So if this equation is satisfying, so from there we found out like, but that is for absolute stability, right? This will give me absolute answer, right? But here what happens if both of them don't cross the -1 point? Then how can I quantify it? How can I quantify it? Both of them are stable, that is fine, both of them are stable, but how can I further quantify which one is more stable, which one is relatively more stable? So I can quantify it like this one. So S1 will be relatively more stable than S2. Why? Because this is more closer to -1 point than this one. Now how can I quantify the closeness to the -1 point? Okay, this I have visualized, but how can I quantify it? Okay, mathematically. So I can quantify using two conditions. One is phase condition and one is magnitude condition. Okay, phase condition and one is magnitude condition. Okay, so this one is this one. Now again, right, we define two frequencies: gain crossover frequency and phase crossover frequency. Crossover, I hope you understand, and this is the phase and gain. The name suggests for itself. Okay, so yeah, we did a question. Okay, and in the next lecture we'll learn about the gain margin, phase margin, and also do a bit of questions from those one. And there, right, the main closeness will come, right? There we'll understand how the closeness is related, right? Here we just found the frequencies at which my gain is 1 or my phase is -1t. Okay, next lecture we'll also get more concept clarity, right? So yeah, thank you for watching this lecture, and do please hit the like button if your concept got clear, and I will see you in the next lecture.